Welcome to another YouTube tutorial on source transformation. If you are looking to master the art of simplifying complex electrical circuits, you have come to the right place. In this tutorial, I will deep dive into the world of source transformation, which is a powerful technique that allows you to convert voltage sources into current sources and vice versa. Whether you are a beginner or an experienced enthusiast, join me as I demystify the process, the step by step, and equip you with the skills to tackle even the trickiest circuit configurations. Let's go. In the last tutorial on superposition, we talked about how we can simplify an electrical circuit by separating the independent sources, getting their independent and individual response to a circuit and adding them together to get the total response. Here, this is another method of circuit analysis and it's called source transformation. Source transformation technique is very useful for simplifying networks or circuits with practical sources. Whenever there is a possibility and requirement to apply source transformation technique for a given circuit, then by applying this technique first and then use any of the methods of analysis based on the requirements so we can solve the network theory problems easily. The technique of transforming one source to another is known as source transformation technique. Voltage source converted to a current source. You might be asking, how is this possible? That is what I want to show you right now. This will help you very well in simplifying your circuits into smaller circuits that you can apply all this simple method of analysis to. In our last tutorial, the last question we treated, I said that I could have used the method of source transformation to simplify it to a single loop so that we can apply Kirchhoff's voltage law and we get our variable of interest, which is Ix. There are two source transformation techniques. The first one is practical voltage source converted into a practical current source. And of course, the second one is the vice versa. The practical current source converted to a practical voltage source. This is a reversible process. So I will explain how that is done. But one advantage of this is that it can be transformed externally, but they are not the same internally. They will be the same externally, but they are not the same internally. I will explain what this means as we use an example to explain everything that is needed for you to understand. So this is the circuit that we'll be using to explain what source transformation is. That is, how do we apply source transformation to solve a circuit, to analyze a circuit. So before I start that, I want to show you that for you to transform a current source to a voltage source, the source must be in parallel with a resistor. What do I mean by that? So I have a voltage source, I have a current source here, right? So I will explain soon where this is applicable. It is called the Thevenin and the Norton's theorem. So in Thevenin and Norton's theorem, we call this the Norton equivalent circuit, where we have a current source in parallel with a resistor. So it can be converted to a voltage source in series with the same resistor. So it's just like we have a source and of course a practical source. A practical source has an internal resistance. So that's why I said this source transformation is used for practical sources, not for ideal. All the circuits and the sources we have been talking about from the beginning of this electrical circuit analysis tutorial, they are ideal sources. Ideal sources are sources that does not obey Ohm's law. Whenever we hear anything ideal in science, it means that they don't exist physically. Because normally a practical source is made with metals. It's made with some materials. And of course, all materials have internal resistances. And if you are not adding an internal resistance, it means that it's just ideal, it's non-ideal. Right? If you are not adding an internal resistance, it means that it's an ideal source. It doesn't happen physically. So a physical current source or a voltage source will have an internal resistance. And here, that is what it is showing us. For a current source, it has an internal resistance, and the internal resistance is usually in parallel with the source, right? It's usually parallel to the source. And for a voltage source, it's usually in series with the voltage source. Do you understand? So, and if you want to convert a current source to a voltage source, it means that your current source must be in parallel with the resistor, and of course the voltage source will be in series with the same resistance. But externally they look the same. That is, if you calculate and you see that the voltage, of course, if you calculate the voltage on the both the resistance and the current source, you see that they still be the same. V is equals to IR. Am I right? V is equals to IR, right? And of course here too, V is also equals to IR, and of course the current flowing through the voltage source and the resistance is what? V over R. But they don't have the same power. They don't absorb the same power. Sorry, they don't dissipate the same power. The current source dissipates a particular amount of power, and this voltage source too dissipates another value of power. So they don't dissipate the same amount of power, and therefore they are not the same internally. So that's one of the shortcomings of this. But we use this to analyze circuits, as it simplifies our work. So let's go with this question. So we have a current source. This is the current source here in parallel with the 5 kilo ohm resistor. So I can use this, I can convert this current source to a voltage source, so that what will I have? So that I will have a single loop circuit. That single loop circuit makes it easy for me to apply Kirchhoff's voltage law. So converting this to V is equals to IR, right? And my current is 9 milliamperes. 9 times 10 to the power minus 3 multiplied by the resistance is 5 kilo ohms times 10 to the power 3. So this gives me 1, right? So it means that voltage is equals to 45 volts. So if I redraw that, so when we convert the current source to the voltage source, this is what it will be. It converts to a voltage source in series with the same resistor. So from here now, I can apply Kirchhoff's voltage law. Applying Kirchhoff's voltage law, of course, I'm looking for the variable I, the current through the circuit. Right, so if I start from this voltage source here, we have minus 45, then plus 5,000 I, that's 5 kilo ohm, plus 4,700 I, plus 3,000 I, then plus 3 volts equals 0. And from here, this is very straightforward to get I. So if we solve that, you can easily get what our I will be. Right, calculating that, combine the like terms, your I should give you 3.307 milliamperes. You can see how simple that is. That simplifies our work. So transform the source, apply KVL, and of course solve your equation. Let me use another example and a more complex circuit to explain how source transformation simplifies a circuit to the simplest form that you can apply your KVL and your KCL to. Let's go. This is the circuit that we'll be using to explain extensively how we can apply source transformation to a circuit. With source transformation, we will simplify the circuit to just a single loop circuit. And after getting a single loop circuit, we apply KVL. It's not every time it will simplify to a single loop circuit, but source transformation will help you simplify it to the simplest circuits that you can apply, maybe node analysis and you get a lot of equations. For example, maybe you can see that in this circuit we have 5 loops. If we are to if we are to apply mesh analysis to this circuit, what do we have? We'll be having 5 equations, right? Applying mesh analysis, we'll be having 5 equations, and that 5 equations, like I told you, the number of equations that I have seen a scientific calculator solve before is 4. So having 5 equations complicates the matter. And of course, how do you want to solve a 5 equation, except you want to use the method of matrices and determinants, which will take a lot of your time. It will take a lot of your time. If you use the Cramer's rule, you can solve the 5 simultaneous equation by solving a 5 by 5 determinant matrix determinant. But that will take a lot of your time. So how then can you do it? Right? So this source transformation simplifies your circuit. So imagine I simplify this circuit, this 5 loop circuit or 5 mesh circuit, to just one loop, and it's just one equation you need to solve. So how would that be? So that makes it very sweet to solve, right? So let's go after it. So look at this section. We have a current source in parallel with a resistor. Here too, we have a current source in parallel with a resistor. And here also, we also have a current source in parallel with a resistor. So let us transform those current sources to voltage sources. So after converting these voltage sources, the voltage sources will be in series with those resistors. So if you transform this current source, what do we have? We have what? V is equals to IR. What is I? 1 amperes multiplied by 9, which is 9 volts. So if you redraw that, what do we have? We have 9 ohms in series with 9 volts. 9 volts, 9 ohms, right? So for this one, what do we do? This is Vx, right? And we have 3 Vx here. So Vx is the voltage on 2 ohms. And of course, Vx is what? 2 multiplied by I, because the current flowing through 2 ohms is what? I. Vx is equals to 2I. So which means that the current on this current source is 3Vx. So 3Vx what? Equals to 6I. That's 3 multiplied by 2I. So if you have to get the voltage that will be transformed from that current source, what do we have? It will be what? 17 multiplied by 6I, which will be what? 102I. Right? So if you draw that, we have what? We have 17 ohms. That is 17 ohms in series with a voltage source, which is what? 102. Sorry, the plus will be here and the negative will be there. And we have 102I. Right? So it remains this part. That is, when we convert 5 ohms and 3 ohms, what do we have? The voltage will be what? 5 times 3, which will be equals to 15 volts. So when we convert that, what do we have? We have 3 ohms in series with 15 volts voltage source. 15 volts. And this is 3 ohms. Right? So let's now redraw the whole circuit using these transformed sources. This is the resultant circuit we have after transforming all the sources. So from here, we have 2 loops, right? We can perform mesh analysis here and get what our I will be. But if you don't want to do mesh analysis, that what you just only want to do is KVL. You want a single loop so that you can just perform KVL in that loop. and that's it. So which means that we need to find a way to transform this 7 ohm so that it will be in series with every component. So how do we do that? So let's combine these 3 ohms and 4 ohms to give us 7 ohms, right? So these two will give us 7 ohms, right? So that we can transform this 15 volts to a current source in parallel with this 7 ohms. So what would that give us? That will give us 15 over 7 I is equals to V over R, which is what? 15 over 7, because 7 is the one parallel to it, right? So which means that we will have a 15 over 7 ampere, 15 over 7 ampere here. Then it will be parallel to 7 ohms and also parallel to another 7 ohms, which is this 7 ohms here. And so forth, right? You can see that we can combine this 7 ohm and 7 ohm in parallel. So when we combine 7 ohm and 7 ohm in parallel, what will be the total resistance? The equivalent resistance will be 7 times 7 over 7 plus 7. I wrote this equation when we did resistance combination in our first video. If you don't understand, you should check it, which is our first video. So we have what? 49 divided by 14, which will give us 3.5 ohms. So which means that we have 15 over 7 amperes in parallel with 3.5 ohms. 15 over 7 amperes in parallel with 3.5 ohms. And therefore we can now convert this back to voltage source so that everything will now be in one loop. So you can see how I simplified this part so that it can give us just one loop. So what will it give us? V is equals to IR. So that's 15 over 7 multiplied by 3.5. So that will give you what? 7.5 volts. So what do we have? We have 7.5 volts in series with 3.5 ohms. 3.5 ohms plus minus 7.5 volts. So this is the equivalent. So let's now redraw this circuit to give us a single loop circuit after simplifying this left hand side. This is the equivalent circuit we now have. You can see how we simplified the large circuit, the complex circuit, to just one loop. You can see how simple it is. This is the complex circuit we are given, right? And this is the equivalent circuit, how we can get the I, by using source transformation, and from here you can apply KVL. So applying KVL, what do we have? If you start from 7.5, you can see it's moving clockwise, so it will be entering the negative of this 7.5 volts voltage source. So that's minus 7.5 volts plus 3.5 I plus, that will not be plus because it has a voltage source and it's entering the negative, right? It will be negative 102 I, and this is a resistor plus 26 I. This is another resistor plus 2 I, and this is a voltage source plus 9 volts, which is equals to 0, right? So what do? We simplify the circuit. So simplifying, what do? We simplify the equation. So simplifying the equation and collecting the like terms, those terms in I, to the left hand side, and those terms that does not have I to the other side, we will get I to be equals to 21.28 milliamperes. That's the current going through the 2 ohm resistor. That is as simple as that. You can see the interesting thing here. The interesting thing here is that we have a complex circuit before and we simplified it to what? A simpler circuit. This complex circuit can be solved using mesh analysis, right? But it will give you 5 equations, and 5 equations is daunting to solve. Solving it to give is requiring you to solve by matrices, in which you can use either the Cramer's rule or you use the adjoint rule. That is finding the adjoint of a 5 by 5 matrix, which is very daunting to solve. So simplifying it to this circuit, and from this circuit you can also use mesh analysis. This the source transformation we did simplify the circuit to a 2-loop circuit, where you can just apply mesh analysis and you get 2 equations and solve 2 simultaneous equations. But we also want to simplify it further. Simplify it further using source transformation, and we got just 1 single equation, which simplified the question for us. That is very simple, and I employ you that if you see a voltage source in series with a resistor, or a current source in parallel with a resistor, right, you can transform the circuit so that you can get a simpler circuit, and then you can employ any method of electrical circuit analysis to the circuit. That simplifies your problem, enable you to use your KVL, your KCL, your node analysis, mesh analysis, and so on. So this is about these are basic circuit analysis techniques you need to do. So the influence and the result of this is on Norton and Thevenin's theorem, and this I will be explaining in the next tutorial. Please click the like button, follow this tutorial as I'll be explaining the Thevenin and Norton's theorem, which are the basis of electrical circuit analysis. If you have any question of what I've touched so far, please drop a comment under this video and I'll make sure I give you the answer that is bothering you. Thank you very much, and see you in the next video.